Okay, so if you're out there and you are getting ready for some senior software engineer technical interviews,
Mm-hmm.
and you're especially thinking about the ones that really dive deep into how you handle and analyze just massive amounts of data,
Yeah,
you are in the perfect place because today we are focusing like a laser beam on these really critical database concepts
absolutely.
that you are going to need to know backwards and forwards for data warehousing and large-scale data processing.
Yeah. When you get to that senior level, they want to know that you're not just storing data.
Right.
They want to know you understand how to make that data sing,
Yeah.
how to get it ready to answer those big important questions.
Right.
And data warehousing is really where all that comes together.
Absolutely. And it is its own world.
Oh, yeah. That's a whole different ballgame.
So our mission today is really clear.
Okay.
We're breaking down the essential storage and aggregation techniques that really make data warehousing tick.
Yep.
By the end of this, you're not only going to understand it, you'll be able to explain it.
You got
Like you're the expert in the room.
That's the goal.
So let's dive in.
Let's do it.
First things first, how is data actually organized at the most basic level?
Okay, so this is like the fundamental fork in the road of database design.
Okay.
We've got row-oriented storage, which is like the classic way.
Mm-hmm.
All the data for one record is right next to each other on the disk.
Okay.
Picture it like an old school ledger.
Okay.
Every detail of a transaction gets its own line, and then you move on to the next one.
Got it. So if we are talking like a table of customer orders,
Right.
row-oriented would be like, okay, this customer's ID, the stuff they ordered where is the total price.
Yeah, all in one block.
One block, and then the next order is right after.
Exactly.
Oh.
Now, column-oriented is like flipping the script.
Okay.
Instead of rows, we're grouping by columns.
Oh,
So all the customer IDs from all the orders are together,
okay.
and all the items, all the addresses, and so it's like each column has its own file almost.
So it's like taking that customer orders table, and instead of rows, it's like sheets for each column.
Yeah, like customer ID, product name, and you've got all the values lined up.
I like that. Okay, so big picture.
Mm-hmm.
When do you pick one over the other?
All right, so it all comes down to what are you doing with the data?
Okay.
Row-oriented is your champion when you're constantly grabbing or changing the whole record.
Okay.
This is your bread and butter for transactional systems.
Uh-huh.
You know, OLTP, online transaction processing.
Right.
Every single transaction, like someone buying something online, you need all the details for that specific order.
Right.
Row-oriented makes that super fast.
Just grab the block, you're good to go.
You got it.
Okay, so what about when we flip to like analyzing tons of historical data? This is where data warehousing comes in, right?
Exactly. That's where column-oriented just takes the trophy.
Yeah.
We call this analytical or OLAP, online analytical processing.
Right.
You're usually looking at a mountain of data, but you only need a few specific pieces to answer a question.
Okay.
Like say you want to know the total revenue for a specific product over a year.
Okay.
You really just need the revenue and the product category columns.
I see. So if those are stored separately, the database is like, I don't even need to look at the rest of it.
That's the beauty of it.
Okay.
You're cutting down the amount of data that needs to move from disk to memory,
Right.
which is usually what slows things down.
That's a huge bottleneck.
Oh, yeah.
Okay, so there's got to be a catch.
Well, there is a trade-off.
Yeah.
If for some reason you need every column from a single row, columnar can be slower.
Okay.
It's got to grab little pieces from all over and put them back together.
Right.
And updates that change multiple columns in a row.
Yeah.
Those are more complex than the just changing it in place that you get with row-oriented.
So for my interview cheat sheet, row-oriented is for transaction-heavy systems where you need that whole row. Column-oriented is for those analytical systems, massive data sets, and you're only looking at a few columns at a time.
You nailed it. And that's why column-oriented is like the king of data warehousing.
Yeah.
It's all about big data and lots of reading and not so much writing.
Right.
It's not uncommon to have fact tables with like hundreds of columns.
Wow.
But then your typical query might just use 4 or 5.
So efficient.
Oh, yeah. And this columnar structure is like the key that unlocks some really cool optimization techniques.
Okay. I'm intrigued. Tell me more.
Well, especially when we talk about data compression.
Oh, yeah. You mentioned that earlier.
Columnar and compression are like best friends.
How so?
It's because the data in a column is so similar.
Yeah.
It's all the same data type, and there's a lot of repetition.
Yeah.
Like, think about a country column in a customer database.
Yeah.
You're going to see the same country codes over and over.
Makes sense.
Compression algorithms love that kind of predictability.
So like when you have similar data, it's way easier to find patterns and squeeze it down?
That's it.
Okay, so are there specific techniques that really work well with this columnar layout?
Absolutely. One of the most powerful is bitmap indexing.
Okay, bitmap indexing. I've heard of that.
Imagine you have a column like product category,
Yep.
and you need to filter by specific categories all the time.
Right.
For each unique category, the database can make a bitmap.
A bitmap.
Yeah, it's a string of bits.
Okay.
Each bit is for a row in your data.
Okay.
A 1 means that row is in that category. A 0 means it's not.
So if we have categories like electronics, books, clothing,
Right.
each one gets its own bitmap.
Exactly.
And if like the 5th bit in the electronics bitmap is a 1,
Yep.
that means the 5th product is an electronic item.
You got it.
Okay, I'm with you.
Now, to make those bitmaps even smaller, especially when you have lots of the same bit in a row.
Which happens, right?
Oh, yeah, especially with fewer unique values.
Okay.
We use something called run length encoding, or RLE.
RLE.
So instead of storing like 00000001011 and on through 0, we can just say 5 zeros, 4 ones, 5 zeros.
It's so much shorter.
Oh, yeah. Way more compact.
Okay, so these compressed bitmaps, they make queries faster too, right?
Well, they're like speed demons for filtering.
How so?
Say you need all records where the category is books.
Mm-hmm.
The database just grabs that pre-made compressed bitmap for books.
Okay.
The ones point right to the rows you need.
And no need to scan the whole column.
Nope, super efficient.
I like it. And what if you have a range query? Or multiple values like categories, electronics, or books?
You can do a bitwise OR on the bitmap. Boom, you've got all the matching rows instantly.
That's awesome.
It's powerful stuff. And for those A and D conditions.
Like multiple filters.
Exactly. Like find all electronics over $100.
Okay, yeah.
If you have bitmaps for both category and price range,
Mm-hmm.
you grab them, do a bitwise A and D.
And you were left with only the ones where both things are true.
You got it. Only the electronics over $100.
And you said counting is super fast too.
Oh, yeah. Counting the ones in a bitmap is lightning fast.
So for all those aggregate queries in analytics,
Perfect match.
bitmap indexes, they're like the multi-tool of data warehousing.
They're pretty awesome.
Oh, but as always, but
There's one catch.
lay it on me.
They don't work as well when you have a column with tons of unique values.
Okay, so high cardinality.
Exactly. The bitmaps get super sparse, mostly zeros,
Right.
and you don't get much compression.
So all those potential benefits kind of disappear.
Pretty much. And updates can be a bit more expensive than traditional indexes, too.
Okay, so high cardinality columns are like the kryptonite of bitmap indexes.
You could say that.
Got it. So we've talked about storage and compression.
Mm-hmm.
Now let's talk about speeding things up even more
Okay.
by pre-calculating and storing aggregations.
This is where data cubes and materialized aggregates come into play.
Okay, data cubes. I've heard that
Right.
thrown around.
They're also called OLAP cubes.
OLAP cubes, right?
And they let you pre-calculate and store those aggregations across multiple dimensions.
Multi-dimensional.
Like time, product, region. It's like a multi-dimensional representation of your data made for slicing and dicing.
Like that.
So back to our sales example.
Sure.
If we want to analyze by date and product, we could build a two-dimensional data cube.
Okay.
One axis is date, the other is product.
So what goes in the cells of this grid?
Each cell would have a pre-calculated measure,
Okay.
like the sum of sales for that specific date and product.
Got it. So the cell for March 15th and widget X.
Yeah.
That's the total revenue from selling widget X on March 15th.
Exactly.
Okay.
And you often see roll-ups or aggregations along a single dimension, too.
Like row and column totals.
Exactly like a spreadsheet.
Okay, what do those mean in a data cube?
So the row totals would be the total sales for that date across all products.
So March 15th, regardless of what was sold, that's the total for the day.
Exactly.
Okay.
Column totals are the total sales for that specific product across all the dates.
So that's the lifetime sales for that product.
You got
And all of this means that certain queries are just blazing fast. I need total sales for yesterday. Boom, data cube has it already.
no need to add up individual transactions.
And you said data cubes can have more than 2 dimensions.
Absolutely. You could add region.
Okay.
Now you've got a 3-dimensional cube.
Wow.
Sales by date, product, and region.
So the core ideas are,
Multiple dimensions,
okay.
pre-calculated aggregations,
Uh-huh.
and often hierarchical structures within those dimensions.
Like year, quarter, month.
Exactly. You can drill up and down.
Okay.
And you've got slicing and dicing.
Slicing and dicing.
Slicing is like focusing on one value of a dimension.
Okay.
Like just sales for Q1 2025.
Got it.
Dicing is picking a subcube by specifying ranges.
So like sales of product A and product B.
Yep.
In region X during Q1 2025.
You got it.
Okay. So the big plus is speed for predefined questions.
Exactly.
What are the downsides?
The main one is flexibility.
Yeah.
Data cubes are designed for specific dimensions and measures. If you need to ask a question that wasn't part of the original plan, you might have to go back to the raw data.
And that's slow.
Yeah, much slower.
Okay.
Like if your cube only tracks total sales, you couldn't suddenly calculate the average discount unless that was included from the start.
So it's all about strategy.
Right.
Most data warehouses keep the raw data for flexibility.
Yep.
And then use these aggregates like data cubes for the common high priority questions.
That's the common pattern.
You mentioned materialized views too.
Oh, yeah.
How do those fit in?
They're kind of similar to data cubes.
Okay.
They store the results of pre-computed queries on disk.
So they speed things up too.
Exactly. But they're not as structured and optimized for multi-dimensional analysis.
Okay.
And they need to be updated when the base data changes.
There's some more overhead.
Yeah, but they're both about making those reads faster.
Right. Just different tools for different jobs.
That's a good way to put it.
Okay, back to column-oriented storage in practice. We know it's great for analytical queries. Anything else I need to know for my interview?
Yeah, remember, even though those fact tables can be massive,
hundreds of columns,
most queries only use a few.
Right.
Columnar storage means you only pay the price for the columns you actually need.
Okay.
And even though it's stored by column, the order of the rows is still there.
Yep.
You can put the full row back together if you need to.
That's good to know.
Yeah. The nth value in each column belongs to the same original row.
I see. So how does sorting work in a columnar world?
Even though it's stored by column, you can still sort the whole thing based on one or more columns. You're reordering the entries within each column file, but in the same way.
Okay, so the columns still match up.
Exactly.
Got it. And sorting can make range queries super fast.
Oh, yeah. Like if you're always filtering sales data by date ranges, sort by date, and those values are all next to each other.
So much faster.
And it helps with compression, too.
Really?
Yeah, if you sort by a column with lots of repetition, those values are all grouped together.
Perfect for run length encoding.
Exactly. The first column you sort by benefits the most.
Okay.
But even sorting the first few helps overall.
For performance and storage.
You got it.
So we've talked a lot about reading data, which is what data warehousing is all about.
Right. Lots of reading, not so much writing.
But what about when you do need to write data to a columnar database?
That's where things get a little trickier.
How so?
All those things that make reads so fast.
Compression sorting.
They make updates harder.
Okay.
Like if you need to change one value in a compressed column, you might have to decompress, change it, and then recompress a whole block.
That doesn't sound fun.
And inserting a new row into a sorted column could mean moving a bunch of data around.
To keep it sorted.
Exactly. So it's different from a row-oriented database.
Where you can just go right to the row you need.
Yep.
Okay, so how do they solve that?
One common way is to use something called LSM trees.
LSM trees, what are those?
They stand for log-structured merge trees.
Log-structured merge trees. Okay.
And the idea is that writes go to an in-memory store first.
Okay.
The in-memory store is optimized for fast writes.
Uh-huh.
And it doesn't have to be columnar right away.
Okay.
Then once enough data builds up, it gets merged with the on-disk column files in the background.
Like a batch process?
Exactly. And that's when the sorting and compression happen.
So it's more efficient to do it all at once.
That's more efficient.
Okay. So when a query comes in, it might need to look at both places.
Yeah, both the on-disk files and the in-memory buffer.
But the user doesn't see any of that complexity.
Nope. The query engine handles it all behind the scenes.
Okay.
The user just sees the most up-to-date data.
Even if it's still being merged.
Exactly.
So LSM trees are like the secret sauce.
Pretty much.
That lets columnar databases handle both reads and writes.
You got it. Efficient reads and reasonable writes.
That's awesome. Okay, so quick recap for everyone getting ready for their senior interviews. We talked about the difference between row and column-oriented storage and how columnar is the clear winner for analytical workloads.
Absolutely.
Then we got into those powerful compression techniques.
Bitmap indexing, run length encoding.
They make storage and queries faster.
Yeah, they're awesome.
And we talked about data cubes.
OLFP cubes for pre-calculating and storing aggregations.
Makes those common analytical queries super fast.
I like lightning.
So if you understand these things,
The storage layout.
compression strategies,
And the pre-aggregation techniques.
You're in a great position to talk about database design and optimization
Especially at that senior level.
when they're throwing those big data analytics questions at you.
Absolutely.
Now, here's a final thought to ponder.
Okay.
Given everything we talked about today, about row versus column-oriented, can you think of any scenarios where you might actually argue for a row-oriented database,
Interesting.
even if the system seems like it's mostly for analytics? Think about the query patterns,
Okay.
the data characteristics, the frequency of updates.
Yeah.
What would make you go against the grain and choose row-oriented?
That's a good one to think about.
Thanks for joining us for this deep dive.